All right, today we are diving into a true monster of a chip. Intel has officially pulled back the curtain on its next-gen server CPU, codenamed Clearwater Forest, and believe me, it is a massive, massive leap forward.
Just look at this number, 288. Let that sink in for a second. That's the number of high-efficiency cores Intel is cramming onto a single processor. Now, to give you some perspective, that's exactly double what its predecessor, Sierra Forest, had. This isn't just a little bump, it's a whole new scale.
So this brings up a couple of really big questions, right? First, how did Intel's engineers even pull this off? How do you build a chip this dense? And maybe more importantly, what does all this power actually mean for the data centers that basically run our entire digital world? So let's peel this onion back layer by layer.
Okay, first, let's just set the stage. The arrival of a 288-core CPU, it's not just about bragging rights with a bigger number. No, it's a signal that the entire playbook for building powerful, efficient servers is changing, and Intel is making a huge bet on a totally new way of thinking.
So how on earth do you build something so incredibly complex? Well, you definitely don't try to make it as one giant, single piece. That would be almost impossible. Instead, you build it using smaller, specialized blocks. You got to think of it like building with the most advanced Legos you've ever seen. Now, this strategy actually has a name. It's called chiplet design. So instead of one massive monolithic chip that's really expensive and difficult to manufacture without flaws, you create these smaller, more manageable chiplets, or tiles, which is what Intel calls them, and then you assemble them into one superprocessor. It's just a much smarter, more flexible way to build.
And this is where Intel's strategy gets really clever. See, they don't make all the Legos the same way. The brains, the 12 compute tiles that have all the actual CPU cores, those are built on their absolute cutting-edge Intel 18A process. But the base tiles and the I/O tiles, which handle things like memory and connecting to the outside world, they're built on older, more mature processes. This whole right node for the job approach is brilliant for optimizing cost and making sure everything actually works.
Okay, so we've got our Lego blocks, but now, how do you connect them? This is where Clearwater Forest really makes a leap, going from something like a sprawling city to a super dense, vertical skyscraper.
In the past, you'd lay all these chiplets out side by side, in 2D. It works, sure, but it takes up a lot of space, and the data has to travel farther, which makes things slower. But with their new Foveros Direct technology, Intel is stacking the compute tiles directly on top of the base tiles. It is a true 3D design.
And that analogy is just perfect. The base and I/O tiles are like the foundational city block, and then the compute tiles are the skyscrapers shooting right up from it. This vertical design gives you incredible density and much, much shorter and faster pathways for all the data to zip between them.
So what's the magic that makes this 3D stacking possible? It's a technique called direct copper-to-copper bonding. We're not talking about old-school solder bumps here. This is about connecting the chips directly to each other with these incredibly tiny, precise connections that are just 9 micrometers apart. This is the tech that makes the whole skyscraper possible.
And all of that leads to a ridiculously important number, the energy cost. Because of that direct copper bonding, sending a single bit of data between the stacked layers costs just 0.05 picojoules. That is an astonishingly small amount of energy. And that extreme efficiency is what prevents the chip from basically melting down from its own internal chatter, unlocking the insane bandwidth you need to feed all 288 cores.
Now that we get the structure, let's zoom in on the most important Lego blocks in the whole thing, the compute tiles themselves and the tiny engines inside them that are doing all the heavy lifting.
The power packed into these tiles really comes from two fundamental breakthroughs. First is the advanced manufacturing process they're built on, which is Intel 18A. And second is the brand new E-core design itself, which is called the Darkmont architecture. Intel 18A is a huge deal. It introduces something called RibbonFET, which is a new type of transistor that gives you way better control and leaks less power. But even cooler, in my opinion, is PowerVia. Think of it like this. It moves all of a building's messy power lines and plumbing into the basement. This frees up all the main floors for one thing and one thing only, high-speed data traffic. It just makes everything faster and way more efficient.
And then you've got the Darkmont core itself, which Intel's own architects are calling a tiny beast. This table tells you why. Compared to the last generation, it has a 50% wider front door for instructions, a workbench that's over 60% bigger to juggle tasks, and it literally has double the number of tools for basic math. To call this an efficiency core almost feels like an insult. This thing is a seriously capable processor on its own.
So, when you add up all those architectural upgrades, what's the result? You get a 17% increase in instructions per cycle, or IPC. That means for every single tick of the clock, each one of those 288 cores can get 17% more work done than the one before it. That is a gigantic gain in single-core capability.
Okay, I know we've gone through a lot of tech. 3D stacking, new transistors, wider cores. But what does it all really add up to? Let's connect all this back to the real world and see what the actual payoff is. Well, all those innovations we just talked about combine to deliver a staggering 1.9x performance uplift compared to the previous generation. We're talking nearly double the performance in the same power envelope. That's the kind of generational leap that can completely change the economics of running a data center.
And here's what that performance leap looks like in the real world. Intel says you can get an 8-to-1 server consolidation. That means a single server with one of these Clearwater Forest CPUs can replace 8 servers that are just 5 years old. Think about that. 8 racks of gear condensed down to just 1.
The impact on power consumption is just as dramatic. If you make that 8-to-1 upgrade in a data center cluster, you could cut power use by up to 750 kilowatts. That's a massive saving in operating costs, and it's a huge step forward for sustainability.
But you know, the key metric for any modern data center, the holy grail, is performance per watt. How much work can you get done for every bit of energy you use? For customers upgrading from those 5-year-old systems, Clearwater Forest delivers a 3.5 times improvement. This is the number that gets people really excited.
So who is all this for? Well, it's for the giant cloud providers that power our apps and our websites. It's for running AI models much more efficiently. It's for the 5G networks connecting our phones and the content delivery networks that stream all our videos. This kind of incredible density is exactly what these massive, scale-out services need to get more powerful and more efficient.
So what's the big takeaway here? This isn't just about faster servers. It's about a fundamental shift in what's even possible. We now have the raw computing power of an entire server rack from just 5 years ago condensed into a single chip. And that just makes you wonder, with this kind of power on our hands, what new applications and discoveries are we going to unlock? What will we build next?